major corporation is building a complex of homes, office, schools, and stores, and we are looking for the rate at which Glen Clove's population is changing with respect to time. And let's underline a couple of things. The population is given in terms of thousands, and T represents years. If we're looking for the rate of change, and it doesn't give us a specific value to find the rate of change. It just says find the rate of change. So in this case, we're going to just find the general derivative. So we're going to find the rate of change, how the population is changing with respect to time. So we have a fraction, we have a variable at the top and a variable at the bottom. Since we have a fraction of these two little mini functions, then we will use the quotient rule in order to determine the derivative. Okay, so remember, we can't just take the top derivative of the top, derivative of the bottom, and divide the derivatives. It's going to be the denominator, as is, times the derivative of the numerator. So our numerator is 25t squared, so the derivative of that would be 50t. And we have 125t, so that would be plus 125. And the derivative of 200, since that's a constant, that would be 0, so we don't have to add in a 0. Minus the numerator as is, and I'm going to put that in parentheses, times the derivative of the denominator. So our denominator, t squared, so we get 2t, plus 5t, the derivative of that would be 5. And of course the derivative of 40 is a 0, that's a constant, so we don't have to write that. So there's the top of our quotient rule, and for the bottom we would take the denominator as is and write that squared. Right. So we're asked to find out what the population will be after 10 years. So we are looking for two things. First of all, we're looking to plug t into the original equation to find the general population at that time. And then we are asked to find the rate of change at that point. So since we're asked to actually use the function, the derivative here, I'm going to clean this up a little bit. Here's where the little bit of that algebra work comes in. So the calculus there, not too bad. The algebra, if I want to simplify this, now to be clear, you could plug a t everywhere, a 10 everywhere you see a t right now. It might not be the easiest thing to plug into the calculator, but you could do that. Or you could also simplify. So I'm just going to show what the work would look like if we simplified this derivative. So we have a trinomial times a binomial, which means we're going to have to do a double distribution. So I'm going to take 50t and I'm going to multiply it times each term in the trinomial. So that would be 50t cubed plus 250t squared plus, and that would give me 2000t. Alright. Then I'm going to do the same thing with the second term in the binomial. I'm going to multiply that 125 times each term in the trinomial. So that would be plus 125t squared plus 625t plus, and so I do 40 times 125, I get 5,000. Okay. And then we're going to subtract from this, so I'm just going to put minus. So here's what we get for that first part of multiplying out. Minus, and let's do the same thing with the second group. So we're going to multiply this trinomial times this binomial. So I would get 50t cubed plus 250t squared plus 400t And then I'm going to distribute the positive 5 as well. So I'm going to distribute the 5. Okay, so that would be positive 125t squared plus 625t plus 1000. Okay, and of course that's all over that denominator squared, but I'm going to hold off on that part for a minute. And remember that we're subtracting off, so all the signs in the second group are going to change to be negative. So we want to keep that in mind. So what we get is 50t cubed minus 50t cubed, 250t squared minus 250t squared, 125t, and then remember minus 125t squared, so those cancel. 625t minus 625t, those cancel as well. And so what we're left with then is 2000t minus 400t, which leaves us with 1600t. So we got that. And then we have 5000 minus 1000. So that would be plus 4000. And that's all over that denominator squared. So we can simplify the numerator a little bit before we plug in the 10. All right. So this would be our simplified form of that derivative. Now, we are asked to do two things for part B, and I'm going to scroll up a little bit for part B. So that was our part A. Part B asks us two things. It says, what will the population be after 10 years? The first question is not dealing with a rate of change. It just says, what is the exact population if you plug a 10 in place of t into our original equation? So that original function, I'm going to plug a 10 in place of t. All right. And I'm going to throw all that in my calculator as is. And one thing you want to be careful about, if you do throw it all in without doing any simplification, that you do need, and I'll put parentheses, you do need an extra set of parentheses around the numerator and an extra set of parentheses around the denominator. Or you could put the entire numerator in first and then find out what the denominator is and then do the division separately. But if I just throw it all into my calculator here, I get 20.78947 and so on. I'm going to go ahead, we're talking about population, I'm going to go ahead and round to the nearest value, the nearest one person. So t is given to us in thousands. Okay, so I'm going to make note of that. This is thousands. In order to convert this to the actual value, I'm going to multiply by 1,000. So that moves my decimal place over 3 spaces. And I'm going to round to the nearest whole person. So let's say that gives me 20,789. Right? So if I round to the nearest whole person, that's what I would get. Okay, so there's 20,000, a little over 20,000 people that live in this community 10 years after the community is formed. Now the second part for question B says, at what rate is the population increasing in the 10th year? So in that 10th year, the population is actually rising within the community, and by how many people? How many people per year is what we're interested in. So we're going to take the derivative that we formed, and we're going to plug now 10 into the derivative to find the rate of change. So 1,600 times 10 plus 4,000. And then I'm going to do 10 squared plus 5 times 10 plus 40. And then I'm going to square that result. All right. Once again, if you put this into your calculator at all at the same time, you need an extra set of parentheses around the numerator. And the denominator already has that set of parentheses around it, so you can type that in as is. All right, and I get 0.554016662 approximately when I put that into my calculator. So this is this many thousand people added to the community per year. Okay, so remember it's difference in population over the difference in time. So change in population over change in time. So the population is increasing. It's positive. And we can think about this in the thousands. That means I can think about how many actual people. So that would be multiplying the top number by 1,000. I could get 554 people, approximately, rounding to the nearest whole person. That's 554 people that are coming into the community per year. So that's our rate of change of population over time.